Hello everybody, this is Imre Baranik talking here. It's my pleasure to introduce Luis Montejano for the next talk of the GEOTOP seminar, which is a web seminar. The topic is fantastic. It's an old conjecture of Banach, and the further steps in its complete solution. The title is on the isometric Banach conjecture, and it is Luis and co-authors, and Luis is famous for using topology, geometry, and combinatorics together, and this is that type of result that he's going to talk about, mixed with Lie groups and Lie algebra. So let's go and listen to him. There is one error on the screen, namely it's February 21 and not February 2, but that I forgive you for that. Okay, so let's start the talk.
Okay. Okay, thank you very much, Imre. So let me start with this talk. Almost 90 years ago, in 1932, Banach stated the following conjecture. Suppose B is a Banach space over the reals or over the complex, it doesn't matter. And suppose all n-dimensional subspaces of B are isometric. These are essentially the same. Can you prove that B is a Hilbert space? The conjecture is true in the following cases. When B is a real Banach space of infinite dimension. It was proved by Borensky in 1960. When B is an infinite dimensional complex Banach space. Vitali-Milman extended Borensky proof in 1970. And finally, in 1977, Gromov proved that the conjecture is true when n is an even integer. Recall that n is the dimension of the sections. Since these results, during the last 50 years, there has not been a real improvement, a real advance in the solution of this conjecture. Then the purpose of this talk is to announce and to give the main ideas of the proof that the conjecture is true if B is a real finite dimensional Banach space and n is congruent to 1 modulo 4. There is a possible exception, which is n equals 133. This is very strange but it is due the existence of a very exceptional Lie algebra called it 7. We will see the reason in a few minutes. Well, the first step is we have to translate the Banach conjecture to a geometric problem. Let's do it. Two Banach spaces are isometric if they are really the same. If there's a bijection, a linear bijection between the first and the second that preserves the norm. But preserving the norm means in this case that the unit ball of the first one goes exactly to the unit ball of the second. So, summarizing, two Banach spaces B1 and B2 are isometric if their corresponding unit balls are afffinely equivalent or linearly equivalent, as you wish. Second, a Banach space is a Hilbert space if and only if B is isometric to the Euclidean space. So if B is a finite dimensional Banach space, B is a Hilbert space if and only if it is if its unit ball is an ellipsoid. Finally, we have to say that this problem is really a codimension 1 problem. This is so because if for some integer n all its subspaces are Hilbert spaces, then the Banach space is a Hilbert space. So the problem is really a codimension 1 problem. And now let's traduce this conjecture to a geometric conjecture. Suppose you have a centrally symmetric convex body in Euclidean n+1 space. And you should think this convex set as the unit ball of the Banach space. So every time that you have a hyperplane, two hyperplanes, these are subspaces, and the unit ball for these subspaces are the corresponding sections. So the hypothesis that they are isometric is essentially the same, that these two sections are affinely equivalent. That means there's a linear map that sends this section to the second section. And this happens for any two sections of this convex body. And the conjecture is that this convex body has to be an ellipsoid. Now, in order to explain the proof of the main ideas of the solution, let's think in a slightly more simple problem. And this is the same problem, but instead of asking the sections to be affinely equivalent, let's ask them to be congruent. So this is a little bit more simpler. Suppose you have in Rn+1 a convex body with the property that all his n-dimensional hyperplane sections through the origin are congruent, are exactly the same convex body. Then this body must be a ball. The second step in the solution is, under these circumstances, under this hypothesis, what can we say about the sections? What are the shape of the possible sections? So here is where the topology enters. So let's take this possible convex body, all whose sections are exactly the same convex body. And now, as in this picture, take a direction, take a section, the blue one, and translate this section until it's tangent to the sphere. If we do this in every direction, we are going to put in every tangent space of the sphere a copy of the same convex body, because all the sections are exactly the same, are congruent. So we are putting in every tangent space a copy of a fixed convex body. For example, one example will be, suppose you are in dimension 2, you have the sphere of dimension 2, and you want to put in every tangent space an equilateral triangle. And then we should have one equilateral triangle in every tangent space, and this triangle should vary continuously all over the sphere. This gives rise to the following formal definition. Let us think in K, a convex set in Rn, Sn. In this case, K, you may think K as a triangle. Then a field of convex bodies tangent to Sn and congruent to K is a continuous function K of u defined for every point of the sphere, where K of u is a congruent copy of K lying the hyperplane tangent to Sn at u. That means we are putting an equilateral triangle in every point of the sphere, in every tangent hyperplane of the sphere. Is it possible to do that? For example, let's try to put a triangle, and let me tell you that it is impossible to put a triangle in the two-dimensional sphere. It is not possible to put also an ellipsoid, for example. Of course, we can put a disk, but it is well known that it is impossible to put even a vector, because it is a very well-known theorem of topology that there is not a field of tangent vectors to the sphere of dimension 2. So the problem now is, given a convex set K and the sphere Sn, when is a field of convex bodies tangent to Sn and congruent to K? When can we put K in every tangent, a copy of K in every tangent plane of the sphere, in such a way that all these copies varies continuously? And then the solution, let me tell you the solution immediately. If the dimension of the sphere is even, then it is impossible to put a convex body tangentially and continually all over the sphere, except, of course, if the convex body is the n ball, in whose case is trivial. If n is equals to 3 and 7, then the tangent space of the sphere of dimension 3 and 7 is parallelizable. It's a product. So you can do this for every k you wish. If n is equals to 1 modulo 4, with the possible exception of 133, we are going to prove that if you can put k tangentially and continuously all over the sphere, then k is going to be a body of revolution. So let me explain why, the reason for that. Let me be a little, let me be a little more technical. So given a convex body K in Rn is going to be the tangent, the dimension of the tangent plane. We're going to say that there's a field of convex bodies congruent to K and tangent to the sphere, if and only if the structure group of the fiber bundle of tangent planes to Sn can be reduced to the group of symmetries of K. So consider all possible isometries of K with fixed K. So if this group can be reduced, then we are going then by definition there's a field of convex body congruent to K and tangent to Sn. Or equivalent, if the characteristic map of the tangent sphere, the tangent space of the sphere, which is a continuous map from the n-1 sphere to the group of isometries of n-dimensional isometries, can be factorized through Gk, the group of the symmetries of K. If this is so, we are going to say that the sphere Sn admits a Gk structure. This is too technical, and let me try to explain what's happening here. We want to put a copy of K in every tangent plane of the sphere. So let's do the following. The tangent plane of the sphere, for the tangent plane of the sphere, we have a tangent plane for every point. So naively, this space should be the sphere Sn cross Rn. But this only happens if n is equal to 1, 3, and 7. For dimension 2, for example, it is true that every point of the sphere has a tangent plane. But the whole system of planes is not the product. Like the Mobius band, there's a twist here. So let's consider all the tangent planes to the north hemisphere, and this is a product. And let's consider the tangent planes to the south hemisphere, and this is again a product of the south hemisphere cross Rn. In this picture, for every point of the sphere, we have a copy here of Rn, which is in the picture of dimension 1. And then, in the equator, we have for every point of the sphere, in the upper sphere, copy of Rn, and in the south hemisphere, a copy of Rn. And we have to glue the equator cross Rn with the equator cross Rn, fiber to fiber, with an isometry. And this isometry has to change around the sphere, around the equator. So what we have is a gluing map that sends Sn cross Rn into Sn cross Rn, and which is fiber-wise preserving, which means for every point of Sn, we have an isometry from Rn to Rn. This gives rise to a map from Sn-1 to SON. This is the gluing map. If you do this correctly, when you glue, you obtain precisely the tangent space of the sphere. If you use to glue this if you glue these two pieces with any other map, and this map is homotopic to this characteristic map, you obtain again the sphere, the tangent space to the sphere. So now let us take in the north hemisphere a copy of K in every fiber. We can do it taking just K cross Rn. The north hemisphere cross K. For every fiber, we take a copy of K in Rn. And the same in the south hemisphere. If when you glue every fiber to every fiber with an isotopy that sends K to K, then what you are going to get is a copy of K in every fiber. And furthermore, if this map is homotopic to the characteristic map, what you obtain here is the tangent space to the sphere and one copy of K in every fiber, which is precisely what we want. So the definition, this implies that we can put a copy of K in every plane, in every tangent plane of Sn continuously, if and only if the characteristic map of this tangent sphere, the tangent space of the sphere, can be factorized through the group of symmetries of K. And with this is now very easy. With these ideas, it's now very easy to prove the first part of the Gromov problem. And this is the following. Suppose K is a convex body and N is even. And suppose we want to put K tangentially and continuously all over the sphere, in every plane of the sphere. And we want to see if K can be, we can do this with K or not. Let me show you that it is, if N is even, it is impossible to do that unless K is a ball. And the proof is extremely simple. Let us take the characteristic map of the sphere, which goes from the n-1 sphere to the group of isometries of Rn. And let us evaluate in one point. This gives rise a map from Sn-1 to Sn-1. And it is well known, it's very easy to see that if the degree of this map when n is even is 2. And unfortunately, the degree of this map when n is odd is 0. It's a null homotopic map. But in the case n is equals to even, it's very easy to see that the degree of this map is even. And now let's suppose that we can put that there's a field of convex body congruent to K and tangent to Sn. Then this means that the symmetry group of K, this map, the characteristic map, can be factorized through this map. Then this means that the inclusion, we have the inclusion here, a map F from the sphere to GK, and this is homotopic. This triangle commutes up to homotopy. On the other hand, we have here the inclusion and the evaluation. And here, suppose K is not a ball. If K is not a ball, then the group of symmetries cannot be transitive, cannot be sent one point to any other. So if this map is not, this composition is just the evaluation in G, then if this is not transitive, this map is not even projective. Then this composition, which is here, is not homotopic, and this is a contradiction to the fact that this map has degree 2. Anyway, this kind of classic proof in topology proves that when n is equals to even, if we have an even sphere, this procedure to put convex bodies in the tangent planes of the sphere is impossible unless what you put is a ball. What happened in dimension n equals congruent to 1 modulo 4? In this case, you have to struggle a little to prove that if you want to do the same, so necessarily you have to put, this time, maybe not a ball, but you have a little more chances. You can put a body of revolution. In other words, if n is congruent to 1 modulo 4, and you can put k tangentially and continuously all over the sphere, then k has to be a body of revolution, necessarily a body of revolution. And so let me give you the idea of this proof. This is where the topology of compound Lie groups enter heavily. We divide the proof in 2 cases. When the group of symmetries is reducible, means it lives in invariant sums of a space, and when G is irreducible, that means G does not live fixed any subspace. So let me give the main ideas of the proof. If n is equals to 1 modulo 4, let's say n is equals of the form 4k plus 1, the tangent space is well known from the 40s that the tangent space Sn can be decomposed into bundles. One which is a line bundle, and the other which is a bundle of dimension 4k. In other words, what we have is in every tangent space of the sphere a line, and all these lines varies continuously all over the sphere and give rise to this one-dimensional bundle. And the complement, the orthogonal, is a 4k dimensional bundle. This 4k dimensional bundle has a very strong structure, has a complex structure. And this is very, very strong. In fact, the principal associated bundle of this second 4k dimensional bundle is the one which is obtained when you take the quotient between SU to k plus 1 and SU to k. Here SU is the group of complex isometries. And then this bundle, the one which is here, resembles very much as the tangent space of the sphere, but over the complex. So it's very easy to prove. It comes from the ideas of Steenrod, from the Steenrod book. It can even be an exercise of the book, that there is not a vector field, neither is a structure group can be reduced. So this means that if G, the group of symmetries of K, leaves fixed some subspace, this subspace has to be a line, and what you have is that K has to be a body of revolution. Here is where the bodies of revolution arrive. And the other case, which is technically more difficult, is that when the group of symmetries is irreducible. It means it does not live invariant any subspace. So let's take G, a irreducible group, with the property that Sn admits a G structure. There's a lot of work in this area, the topology of compact Lie groups, regarding this. Especially there are 2 papers in 1971 and a few years ago, in which the authors prove give a lot of information about this situation. The first one is that if G is irreducible, but the sphere Sn admits a G structure, then G has to be a simple Lie group. This is a very complicated proof, very technical. The second one is that G cannot be a classical group. It means G has to be either all SON, and if not, it cannot be a classical group. For example, it cannot be SOK or SUK, or the one that comes from it cannot be the orthogonal group for the reals, the conflicts, or the quaternions. And the third step is that the dimension of G, using abstraction theory, you can prove, it's an easy proof this time, that the dimension of G cannot be so small with respect to M. If this is true, then if G cannot be a classical group but has to be simple, then G has to be either one of the special Lie groups, one of these 5 special Lie groups, G2, F4, X6, E7, or E8, or it has to be a spin group. We were able to prove in this paper that under these circumstances, Sn admits a G structure and G is reducible. If G is a spin group, then the dimension of N has to be even. And we are in dimension 4k plus 1, odd dimension. So we can discard this possibility. On the other hand, we know that the dimension of G cannot be very small with respect to N. And then there's here a list of where these exceptional groups, who has been studied for many, many years, they are very interesting, admits an irreducible representation in a space of dimension N. Then if you look here, for example, G2, it has dimension 14, but it admits a representation in some Rn of the form 4k plus 1 until 77. Then we already know that dimension of G cannot be too small with respect to the dimension of N. This means that G2, this sphere, cannot admits a G2 structure. The same happens with F4 because we have 52.73, with E6, with E8, but we have a problem exactly here. Then it is possible that there exists a group, that there exists a copy of this E7 and a G structure of this E7 structure of the sphere Sn, such that E7 is irreducible. And this is why the exceptional case. And now this explained, let me go, this gives an idea of how the topology of compact Lie groups is used to prove the following. You want to know if there's a field of convex bodies tangent to the sphere and conjugate and congruent to K. And then the solution is, if N is even, K has to be a ball. And if N is congruent to 1 modulo 4, has to be a body of revolution with the possible section of 133. And so let's come back to our problem. What we have here is a convex body with the property that all his hyperplane sections are affinely equivalent. This time, they are not congruent, but affinely equivalent. And this time, we can follow the same ideas. We can take our body and push every section until it's tangent. And so what we get is, in every tangent space, a convex body, and all these convex bodies this time are not going to be congruent, but are going to be all affinely equivalent. This is technically has exactly, it's a little bit more abstract, but it's technically the same thing. The same ideas that we were working works here to prove that if n is even, these sections have to be ellipsoid. If n is equals to 3 and 7, there is not information. And if n is equals to 1 modulo 4, then the sections have to be an affine copy of a body of revolution. So let's see what can we do with this. So the third step is to conclude that our convex body, that means the unit ball of our Banach space, is an ellipsoid from the fact that all its sections through the origin are affine bodies of revolution. And here is where the convex geometry ideas arrive. So let's speak a little bit about convexity and about the bodies of revolution. So what's a body of revolution? A body of revolution is a convex body with the property that there's an axis, a line L, and perpendicular to this line L, every section is a ball. At the centers of all these balls lies in the line. So it has a rotational symmetry. It is not very difficult to prove an exercise, but a little surprising, that every section of a body of revolution is again a body of revolution. It's not difficult to prove, but it's strange. Every section of a body of revolution is a body of revolution. And then the problem is the converse true? In particular, we have the following problem. Suppose we had a centrally symmetric convex body. Let's put dimension n greater than 3. And suppose every n section of K through the origin is a body of revolution. Is K a body of revolution? To my knowledge, nobody knows the answer. I tried to prove this theorem, but I was not able to do it. In fact, 35 years ago, I tried to prove this problem in the three-dimensional case, because this problem was very close to a conjecture of Versteeg. And I was, in this case, also unable to prove the theorem. And I was very sad because I was able to prove just a little simple thing. And this little thing is the following one. If you have a convex body and all its sections are bodies of revolution, I cannot prove that this body is a body of revolution, but I can prove that one of these sections, as it should be, is a ball. And this time, this will be enough for our purposes. So here we have this theorem, let K be a centrally symmetric convex body, n greater than 3. And suppose every n section of K through the origin is a body of revolution. Then there is a next section through the origin, which is a ball. The dimension of the theorem is n greater than 3. I don't know what happens for n equals 3, for example. I doubt this is true. In any case, the proof of this theorem is perhaps, regarding the proof of this conjecture, the most original part of the work. Somehow, all the others think is to use very heavy machinery, very heavy tools from topology of compactly groups. But here in the proof of this theorem is where the most original ideas arrive regarding the proof of this conjecture. So let's come back again with the proof of the conjecture. So suppose we have a convex body in Rn, which is centrally symmetric, and suppose the dimension of the body is 4k plus 1 is congruent to n is 4k plus 1. We are, suppose as hypothesis, all hyperplane sections are affinely equivalent. So if all sections are affinely equivalent, all this topology proves that the sections have to be affinely equivalent. All the sections are affinely equivalent, but also all of them are affinely equivalent to a fixed body of revolution. And once you have this hypothesis, the convex geometry proves that these affine bodies of revolution, if all of them are affine bodies of revolution, one of them has to be affinely equivalent to a ball, means an ellipsoid. And if one of them is an ellipsoid, then all the others are ellipsoids. And then it's the classical thing that if all the sections are ellipsoids, so the whole body is an ellipsoid. And this is essentially the proof. So the main theorem is the following one. Let B be a Banach space. And suppose any two n-dimensional subspaces of B are isometric. If n is congruent to 1 modulo 4, then B is a Hilbert space with the possible exception of 133. You want to see more details, it is in archive. The proof is in archive. And now, finally, for the end of this conference, let me discuss a little bit about the complex isometric Banach space. This time the conjecture is exactly the same, except that the Banach space is a complex space. It's a vector space over the complex numbers. So in 1971, Vitaly Milman was able to generalize the ideas of Borensky to prove that if the dimension of B is infinite, the conjecture is true. Furthermore, in the same paper, in 1977, Gromov proved that if n is even and B is a complex Banach space, then the conjecture is true. Furthermore, he also proved that if n is odd, but the codimension is very big, the codimension is greater than n. So let's say the dimension of B is 2n and the dimension of the section is n, then also the conjecture is true. Finally, Javier Bracho and I, had been working lately in the case again when n is congruent to 1 modulo 4 and trying to adapt this proof to the complex case. It turns out that when we are working with the topology of compact Lie groups, it's even easier to do the proof because the complex behaves much easier than the reals. But in the convexity world, especially when you have to work with the ellipsoids, the things are a little weird. Anyway, we think that we are very close to a proof, and we believe the conjecture is true. We are almost sure the conjecture is true. We are very close to, we have to check some details, that the conjecture is true for any congruent to 1 modulo 4, and this time there's not going to be an exceptional 133. The reason is that here in the complex world, the dimension of G is going to be not 2n minus 2, but 2n minus 4. And then this means that in the table, this is not going to be a counterexample. We can discard this example. So with this, let me finish the talk. Muchas gracias. Thank you.
Thank you very much. Thank you. Questions from anyone?
Luis, can you say anything about the exceptional case 133?
Just as I told you, the idea is under the hypothesis, you group, if it's not the whole group of isometries of Sn has to be a Lie group. And for classical work, it cannot be from classical results, it cannot be one of the orthogonal isometric groups over the reals, the complex, or the quaternions. Furthermore, the dimension of G has to be not very small with respect to N. So you are trying to see if there's a counterexample. And you look at the group of isometries, and there's maybe a group of the group of isometries of a counterexample, which is this group E7. This group E7 is a very exceptional Lie group. This is not the first time that this group makes problems to the proof of theorems. This group E7, it has dimensional 133, and is contained in SON is SO 133, and is irreducible. It means it does not fix any subspace of 134. Furthermore, we don't know if Sn admits a G structure when G is equals to E7. This is something that we can handle right now. In any case, there's no way to, with these ideas, to discard this group, and then that's why there's a possible exception in the proof. But I believe it's just a problem of the proof, and it should be true. The other perhaps interesting thing is that what happened with the conjecture when n is equals to congruent to one modulo 3, for example, S3 and S7 and so on, with three-dimensional. Here in this case, the topology, these ideas does not work because the topology is not given information. And I believe that in order to solve the conjecture for these dimensions, I believe that conjecture is true also in this dimension. We have to use somehow analysis. What is missing in this proof is the analysis, and the analysis should enter somewhere if we want to prove the conjecture in dimension 3, for example. Okay.
And the case when n is 3 mod 4.
For example, n and 4. For example, if all three-dimensional sections of a four-dimensional convex body are affinely equivalent, then the body has to be an ellipsoid. If we instead of change the problem, instead of affinely equivalent with congruent, then this body is a ball. And the proof is Schneider, and it uses a lot of analysis. It uses the notion of volume and spherical harmonics and analysis of Fourier. And but this is because when you use congruent and the body is symmetric, you are able to use these ideas of Alexandrov in analysis. But in this case, in which the sections are only affinely equivalent, we don't have the notion, we don't have, in principle, these analysis ideas. And that's why we don't have a proof. So I believe that we only with these ideas of topology, it's impossible to prove it. And somehow the missing ingredient in this dimension is because we need to use some analysis, Fourier, or I don't know, some strange thing that I don't know.
Thank you very much again.